All right, we are going to do question 8A from the midterm, which says, for each of these compounds below, give the number of valence electrons, the molecular electronic ground state, and their bond order. Then, using your calculated bond order, predict which compound for each of the following pairs has the strongest bond. So question A, we're looking at C2 plus and C2. So the very first thing you're going to do is look at just carbon individually. And because carbon has 4 valence electrons, because it's in group 4, we're going to start filling it up. And because of Pauli exclusion principle, we're saying that only 2 electrons can fill each orbital, and they will have opposite spins. So the plus or the up arrow will represent the electron that's spinning up. The down arrow will represent that it's spinning down. And then for up here, we're applying Hund's rule, which just says that due to electron repulsion, we are going to fill the same subshell but different orbitals with parallel spins. So these are spinning up, and they will fill individually before we'll double them up.
We're filling up our hybridization. So the sigma 2s and the sigma antibonding 2s are going to be filled by both of the carbon's 2s shells. So in the center, we're going to have a total of 4 valence electrons. So again, we're going to fill them up with the different spins. And we're going from the lower energy level to the higher energy level. Antibondings are always going to be at a higher energy level, which is why it was filled up second. Now we're going to move on to the P shell. And the P shell here has 2 electrons in each, so there's going to be like 4 valence electrons in the center. We're going to, again, go to the lowest energy level first, which is, in this case, the 2px and the 2py. So we're going to go ahead and fill them up each.
And the x, y, and z in this case represents the orientation of the px, py, and pz planes. It doesn't matter which one you include as long as you have you're consistent throughout your model.
So again, you're going to fill them up just like these ones you did each of the parallel orbitals first, and then you're going to go back and then fill in the opposite spin. So that is basically our completion of the molecular orbital diagram.
So you'll notice that since each carbon had 4 valence electrons and we have 2 of carbons, we have 8 total in the middle.
Oh, also, just to clarify, in carbon's case, Z is less than 8, which is another standard rule. Z is the atomic number, and because the atomic number is less than 8, that makes the sigma 2p orbital at a higher energy level than it would normally be. Normally the 2pz shell or sigma 2p shell would be below the pi bonding, but in this case it's above.
And if you were to do 2 different atoms, so one that has a charge that's greater than 8 and one that's lower than 8, so if we have helium and fluorine, then we would have to do, we would go with the one with the lowest charge, so we would go with this model rather than putting the sigma 2p underneath.
So the question asks us to give the number of valence electrons first. So basically the way we do that is in the hybridization it has a total of both of the electrons from each of the atoms that you're hybridizing. So we have 2, 4, 6, 8 valence electrons.
And then the next question is asking about the molecular electronic ground state. And that's basically where we just go in order from the lowest energy up to the highest energy filled. So we're going to start out with sigma 2s, and there's 2 electrons there. So we're going to put a little exponent of 2. And then we go up to the sigma star 2s2, and then we'll move up to the pi px. There's 2 electrons there, and pi 2p Y2. So that's the molecular electronic ground state of C2.
You could also write it as just pi 2p with a 4 exponent, because the x and the y are not really necessary in this case, because you know that the z is going to be a sigma bond, or the third is going to be a sigma bond.
Because they're all interchangeable orientations. All right, and then the next question is asking about bond order. So for bond order, our equation is 1/2 the bonded electrons, number of bonded, minus the number of antibonding.
So in this case, it's like pretty easy to figure out. We have 2 here and 2 more in each of these, so that makes 6 bonded electrons.
And then we have these 2 right here, which are the only anti-bonded. So we have 1/2 6 minus 2, which is 1/2 of 4, which is 2. So C2 has a bond order of 2.
Okay, so now that we've done all of the questions, or parts of the questions for C2, now we're going to look at the C2 plus component of the question.
So to do the plus, all we're going to have to do is take away an electron from one of the C's. So we'll do it to that one over there.
So because it's positive charge, we're taking away 1 electron. And then we're also going to have to do the same thing in the hybridized shells. So we're going to go ahead and take 1 away from the pi bonds.
So since we took 1 from over there, that means that we now have 2, 4, 6, 7 valence electrons in our C2 plus.
And the molecular electronic ground state is pretty much the same. We're just going to have a little bit of variation. We're still going to have the sigma 2s2, sigma antibonding 2s2. But now, because we're 1 electron short, we're either going to have pi 2px2, pi 2py1, or just pi 2p3.
So now that we've written out our diagram and our molecular electronic ground state, we can now calculate the bond order, which our formula is again 1/2 bonded, number of bonded. So we have 2, 4, 5 bonded minus 2 anti-bonded. So we have 3/2 the bond order.
And the question asks us which has the stronger bond, C2 plus or C2. And the way you figure out which one has the stronger bond is by the bond order. So looking at 2 and 3/2, we see that 2 has the stronger bond order. And because it has a higher bond order, it is a
shorter and stronger bond. So the strongest of our C2 and our C2 plus is going to be our C2, because of the bond order.
If you're ever asked a question on whether it's paramagnetic or diamagnetic, the way you figure that out is based on the number of unpaired electrons. In the case of C2 plus, essentially this is not here. So we have one unpaired electron here, making it paramagnetic.
And that means that it's going to be attracted to the magnetic field. However, when we had just C2 and this was completely filled, that means we have no unpaired electrons. Therefore, it is diamagnetic and it would be repelled by the magnetic field.